Good afternoon, my name's Sandra at Wharton. I've been a maths advisor for somewhere in the region of about 12 years now. I worked with the National Strategies for about 6 years. I was a regional advisor with the National Strategies mathematics team. I also worked with the functional skills team for the National Strategies as well. Since the strategy closed down, I've been doing a similar sort of job, but I've been doing it for myself, so I'm now an independent advisor. I work with schools across the country, including some schools in quite challenging circumstances. So what we're going to talk about this afternoon is what we think the impact's going to be of the new GCSEs on the teaching of mathematics. So the new GCSE, the specification states that students should enable students to develop fluent knowledge, skills and understanding of mathematical methods and concepts, acquire, select and apply mathematical techniques to solve problems, reason mathematically, make deductions and inferences and draw conclusions, comprehend, interpret and communicate mathematical information in a variety of forms. This will be assessed by three assessment objectives, the first one of which, the AO1, is about using and applying standard techniques, AO2, which is about reasoning and interpreting and communicating mathematically, and AO3 is about solving problems within mathematics and other contexts. All the main awarding boards have now been accredited, but Ofqual is still exploring the comparability of some of the sample assessment material. What they're doing is they're doing quite an in-depth statistical analysis of the consistency of the sample material across all the awarding organisations. And they're also looking at increasing the problem-solving element for all of the awarding organisations. As a result of this, we've recently had published by the NCETM, the National Centre for the Excellence of Teaching Mathematics, a paper where they started to look at what was the same and what was different about the awarding material, about the sample material. It's quite hard to actually judge the difference between different examination questions. So what they did was they used a couple of ways of actually looking at how the exam papers might differ. The two categories they used were technical complexity, which is basically just about the knowledge and the skills that the candidates need in order to answer that question. So for example, a question that involved a right-angled triangle, where you were looking for a missing side and you were using SOHCAHTOA, would be classed as having less technical complexity than a question that was a non-right-angled triangle and required the use of the sine or cosine rule. So that's your basic technical complexity. But alongside that, they were also looking at the cognitive burden of any particular question. Now that tends to be a link to how much actual processing of information the students are going to have to do. So for example, an unstructured question is going to be more likely to be more difficult than a question that contains lots of scaffolding. Questions where the method is not suggested or is not clear is also likely to be harder. Questions with lots of information or where there are a few signposts about how you should go about solving the problem are also likely to be more difficult, and also questions where the route through the question is unclear is also likely to be more difficult. And as part of this process, what they actually did was they looked at a few questions. So what I'd like you to do now is we're just going to have a look at a question. I'd like you just to take a minute or so to look at this question and just think to yourself, in terms of technical challenge, remember that's the content, and the cognitive burden, so how much processing of information is required, how complex do you think or how hard is this question? Okay. The NCETM assessment decided that both the technical challenge and the cognitive burden are quite high for this question. The reason being is that you're actually having to do percentages. You're actually calculating percentage increase, and then you're also having to do a reverse percentage. There's no scaffolding, and the route through the question might not be immediately clear. Therefore, it would be classed as quite a high complexity in both categories. Now I'd like you to take a little look at this question and see what you think about the difficulty of this question. In this case, the technical challenge is not very high. It would be higher if it was a non-calculator paper, but it's not particularly high. But the cognitive burden is quite high because you're having to sift through quite a lot of information. It's not signposted or particularly obvious what mathematics you need to use, and the answers have to be cross-referenced and interpreted. So the cognitive burden in this case is quite high. And this is the final example, so again, a minute just to think what you might class this question as. This is an example of a proof question, and therefore actually its technical complexity is quite high, but its cognitive burden is not particularly high because it's fairly obvious what is required and there isn't a lot of information to process either. So technically it's quite difficult, but in terms of the cognitive burden it's not particularly high. So there are more examples as well on the NCETM website that you can have a look at if you would like to have a look at some other comparisons. But basically what was coming out of the comparison was that there was quite a lot of inconsistency among the different awarding organisations as to the complexity of their questions. So what can you expect over the next few months in terms of the response from Ofqual, for example? Well, we believe that you are likely to have to be expecting some more sample material because they are, we believe, working on that at this moment. So you're likely to be seeing some more sample material from each of the awarding organisations. And what you're also likely to have to expect is that they're going to be more consistent. So you're not going to see the same variability between awarding organisations. And I think probably the most important thing is that you are going to see, if anything, an increase in the amount of problem solving or the cognitive burden required of students when completing papers. So therefore, I think I quite like this question actually. You need to think about how you're going to start to prepare for this. And what's interesting about this quote, I really like this quote, is the idea that a problem is not inherent in the task. It's not necessarily a problem, it depends on the individual. So in other words, thinking about that old saying, it's easy when you know how, okay? And you've got to really think about that. So actually thinking about your students, how are you going to compare different students for their experience of the new GCSE? So basically there's two groups really that have got to be at the top of your mind in this process. The first is Year 9. They're going to be the first group of students that come through that will actually need to sit the new GCSE. So what do you need to think about in terms of them? Well, they're already halfway through their 5-year experience of maths teaching. So in their case, what you're probably likely to be thinking about is increasing the amount of explanation, reasoning, justification they need to do, and try and increase the cognitive demand on learners when they're looking at questions. So those are the sorts of things you need to be planning in for Year 9. And then also thinking about Year 7. Year 7 are the first group of students that are hopefully, fingers crossed, are going to go right through their schooling based on this new assessment regime. So they're the ones you can really start from scratch with. So in their case, what you need to be thinking about is actually from Year 7, how can you start to build up the complexity, the familiarity and the independence with which they work with the technical demand that you're also teaching them. So all the time alongside the technical demand, you're thinking about complexity, familiarity and how independently they can work. So what I'd like to do for the rest of this webinar is just actually start to think about some of the resources and some of the research that's out there that you can use to help you in this process. So I think probably one of the resources that would come to everybody's mind when they're thinking about teaching for problem solving in mathematics is the Enrich site. Full of a wide range of problems for different key stages, a fantastic resource. But I think what people also often don't think about when they think about research, Enrich is the amount of research material that's also available on Enrich. So one of the articles that was recently published by Jenny Piggott looked at the idea of the role of problem solving in terms of maths teaching. So there's a number of ways we can actually use problem solving in the classroom. We can use problem solving as a means of learning mathematical content. So actually students are developing their mathematical knowledge as they solve the problem. We can use problem solving in order to teach about the process of problem solving. So that's teaching about. So in that case, your emphasis is not on the mathematical content, but on the problem solving process, the steps that you go through. You can use problem solving as a generic skill that's applicable to other subjects. Every maths teacher I think that's ever existed has been asked the question, why are we learning mathematics? Well, here's an answer for you. It's actually one of the best ways of teaching the generic skills that you need in order to solve problems in real life. So there's an answer to that question. You can use problem solving as a motivational tool, because actually most people like to solve rich problems, so it can be a motivational tool. Or you can solve problem solving as a fundamental part of mathematics. So you can use it for any of those purposes. And when solving problems mathematically, we need to start to think about what it means to think mathematically. And I don't know, some of you may have already read the work of John Mason and certain other people on thinking about the idea of what is mathematical thinking. So here are some of the suggestions that came from sources like John Mason, which are, for example, specialising. So in other words, you start with a very complex problem, and if you can't solve that problem, then what you do is you change it until you can. So you keep simplifying or changing it or specialising it until you get a problem you can solve. Generalising. This is probably the most powerful part of mathematics. There actually has been research to show that people can't function properly in a modern society unless they have the ability to generalise. So generalisation is probably one of the strongest elements of mathematics. Using analogy. This is a really powerful tool. Most of us as experienced mathematicians use analogy. We look at an exam paper and we look at the words and we immediately say, that's a best buy question, or that's a solving simultaneous equations question. We look for similar types of questions. We don't tend to teach students how to do this. So actually teaching them explicitly to look for types of questions is a very powerful tool. Visualising. We don't do that enough. We hardly do any visualising from when they leave primary school to when they start A-level. Whereas a lot of the research suggests that visualising and looking at different representations is one of the most powerful ways of helping students to understand mathematics. In primary schools, they use manipulatives all the time, and then suddenly when they get to year 7, we stop using them. Why do we stop using them? We can still use those to help students with their understanding. Identifying the particular, using questions like sometimes, always, never. When is this true? When is it not true? When is this false? When is it true? Modelling, what are the most important uses of mathematics, and we hardly ever touch on it really in the classroom. And decomposing, so in other words, trying to find out what the essence of a problem is. So instead of presenting the question to students, asking students to try and identify what the question is themselves. So we need to think about how we can identify those mathematical thinking strategies in our teaching. And another resource and thinking about resources that can help us to do that, one of the classic resources out there, which I hope you've all got at the top of your shelf, is the standards unit material. Wonderful resources. I cry every time I go into a school and they're still in the plastic wrappers. So please, I hope they're not in your plastic wrappers. The standards unit material is wonderful material. It's written by Malcolm Swan. You can access it on the STEM library if you haven't got a hard copy. And he uses lots of the strategies outlined on this slide to help students to learn how to think mathematically. So he uses strategies which involve them classifying mathematical objects. interpreting multiple representations, evaluating mathematical statements. Is this true? Is this false? Is it sometimes true? Is it never true? Creating their own problems. This is a really powerful strategy in a classroom. And asking students to create problems that are, create a hard problem, create an easy problem. What makes it easy? What makes it hard? Asking those types of questions and analysing reasoning and solutions. So that starts to build that idea of being able to explain and justify. And what I think a lot of people don't know about the standard unit material is, as well as the actual case studies and the example lessons, is they also have a lot of theory on the pedagogy behind mathematics teaching. They also have a set of CPD units as well that can be used in department meetings, etc. And their lessons are really identify key concepts. So for example, N6 is about proportional reasoning. And when I first taught that unit, I have to say not only did it change the way I teach proportional reasoning, but it also changed the way that I personally think about proportional reasoning. So they are really super set material. We hear a lot at the moment about the what's happening in other countries, what's happening internationally, so Singapore, Shanghai, etc. So another area that's got a lot of resources and interesting research is the PISA site. They did produce some material not too long ago about the PISA, looking at what mathematical literacy actually meant. So what did it mean to be mathematically literate? So therefore what they talked about was the idea of the modelling process. So they talked about students being able to start with a problem that's situated in reality, a question that you want to ask. You know, how many friends have you got on Facebook? How does Facebook work? How many people would you be connected to? Some problem that's based in reality. And then actually organising that problem according to mathematical concepts. So what mathematics would you need to use in order to be able to tackle this problem? And then gradually trimming away the reality, so taking away the extra bits you don't need, simplifying, making assumptions, all these strategies that students need to learn. And then solving the problem mathematically, so using your mathematical toolkit in order to be able to solve the problem, and then taking that back into the real world and saying, does this make sense? Does this model that I've set up actually reflect what happens in reality? And that mathematical process, that modelling process, is something that we need to teach students. This is just one example from the PISA side. There are lots and lots of different examples of really rich open-ended activities. And all of these activities could be used either to teach the different elements of problem solving itself, or to teach students how to think mathematically in the same way that we looked at on the previous slide. So again, that's a site well worth exploring. In terms of how they look at mathematical literacy, what PISA have done is they've split it up into what they call a number of competencies. So the competencies that they describe are thinking and reasoning, argumentation, communication, modelling, problem posing and solving, representation, using symbolic, formal and technical language, and the use of aids and tools. Now what I'm hoping you're starting to see here is a pattern, because this list doesn't look hugely different to me to some of the other lists that we've already looked at today. So although the wording might be dissimilar, I think you can see that all of these research sites, all of these resources are looking at the same types of things. And what PISA also does is it groups these competencies into what they call clusters, and they assess them under clusters. And the clusters they use are starting with reproduction. That cluster is just about students being able to reproduce what they already know, so use the mathematics they already know. The next cluster is about connections, which extends the reproduction cluster a little bit to take in problem solving and more complex situations. And the final cluster is about reflections, which includes them reflecting on the process of the mathematics as well as the mathematics itself. Now, I don't know about you, but those feel to me very much like they reflect the aims of the new GCSE that we looked at right back at the beginning of this webinar. So again, we're looking at a similar set of pattern. So what's your role in this? Well, basically, you've got to start to think about teaching a little bit differently. Again, this is a piece of research from Enrich, which was looking at the role of the teacher when it comes to a problem-solving classroom. So the first thing is you've got to have non-assertive mediation. So in other words, sometimes you've just got to say nothing, and you've got to stand back and you've got to let students sort the problem out for themselves. You've got to encourage group work discussion and communicating, and those lessons tend to be a bit louder than mathematics teachers have generally been used to. You've got to encourage varied solutions and different approaches. Most people, when they're talking about mathematics, if they're not maybe as comfortable about mathematics as they might be, often suggest that mathematics only has one solution and that if you're wrong, you're wrong. Well, actually, that's not true. Mathematics has lots of different varied ways of solving problems. You have to encourage exploration and making connections. Students need to see mathematics as connected. At the moment, they tend to see it as a series of isolated events. And you have to acknowledge that it's hard. It's supposed to be hard, and they're supposed to have to push themselves. They have to go outside their comfort zones. So how do you support them when they are moving outside their comfort zones? Well, thinking about different areas of resources, OCR a few years ago produced some resources for the functional skills pilot, where they started to think about how you would respond to students who are having difficulties. So some of the challenges that students have when they're looking at problem solving is they have trouble making sense of the information they've seen, or they don't know where to start. So what can you do? Well, you can model examples of how to make sense and where to start, and you can encourage class discussions. They can't cope with the amount of reading. Well, teach them strategies such as highlighting, scanning, skimming, etc. They don't understand the need to make assumptions. Model some simple examples for them. They don't understand the idea of more than one answer. Compare different methods. Help them to understand why the different methods might be the same. They don't explain, justify their answers. Again, this is about giving them examples and modelling good practice. So I think what I would like to suggest here is that there's a theme that runs through all of these examples, and it's about teaching students to be able to solve problems. So if I was in your position now, I think what I would be doing is I'd be identifying a few key resources. So for example, colleagues are producing a set of resources that are for supporting the new GCSE framework. The publishers are all doing this, and obviously we've been doing the same. The awarding organisations will also have some key material on their websites. I would then identify 2 or 3 other locations, for example, Enrich, Standard Units, PISA, and then I'd stick with that set of resources. You can spend all your time chasing around looking for resource after resource after resource, whereas actually time is usually better spent by thinking about how you're actually going to use those resources in the classroom, working together to plan collaboratively how you're going to use those resources. So, basically speaking, to be able to be mathematically literate in a modern society, learners need to be confident and fluent with a strong conceptual understanding. They need to be able to reason, interpret and communicate mathematically. They need to be able to use their own mathematical toolkit independently to solve a range of increasingly complex, unfamiliar problems within mathematics and beyond. So I really like this quote, which says, more important than the specific mathematical results are the habits of mind used by the people who create these results. So what I'd like you to think about is, what habits of mind are you creating?